Hello and welcome to Math Zone African Motives. I'm your tutor, and in today's tutorial, we're going to dive into the fascinating world of differentiation, specifically focusing on how to combine various rules to solve complex problems. By the end of this video, you will be able to differentiate complex functions by applying the chain, product, and quotient rules, and you'll learn how to simplify the process using logarithmic differentiation. Let's get started. Our first problem is a proof. We need to prove that if y equals the natural logarithm of the quotient of 1 plus cosine x and sine x, then its derivative, di dx, is equal to negative cosecant x. We'll explore two methods for this. The first is a direct approach using the quotient rule. We'll label this as Method 1, using the chain and quotient rules. Here's the original function we need to differentiate. The first step is to apply the chain rule. The outside function is the natural logarithm, and the inside function is the fraction, 1 plus c cos x, sin x. So we differentiate the natural log, which gives us 1 over the inside function, and then multiply by the derivative of that inside function. Now, we need to find the derivative of the fraction. This requires the quotient rule. The quotient rule states that for a function f divided by g, the derivative is gi times the derivative of f minus f times the derivative of g, all divided by g, squared. Let's identify f and g for our problem. We'll set f equal to the numerator, 1 plus cosine x, and g equal to the denominator, sine x. Next, we find their derivatives. The derivative of 1 plus cosine x is negative sine x, since the derivative of 1 is 0, and the derivative of cosine x is negative sine x. The derivative of sine x is simply cosine x. Now we substitute these into our chain rule equation. The first part simplifies to sine x over 1 plus cosine x. The second part is the result of applying the quotient rule. We have the derivative of the inside function. The first term is sine x times negative sine x, and the second term is negative of the product of 1 plus cosine x and cosine x, all over sine x squared. Now we simplify. We can factor a negative sign out of the numerator of the second fraction. This gives us negative of sine squared x plus cosine squared x. We should remember that sine squared x plus cosine squared x is a fundamental trigonometric identity equal to 1. Substituting 1 for sine squared x plus cosine squared x, we get 1 plus cosine x inside the brackets. Now we have sine x over 1 plus cosine x, multiplied by negative of 1 plus cosine x, all over sin x squared. Look closely. We have the term 1 plus chi cos x in both the denominator of the first fraction and the numerator of the second fraction. We can cancel it out. Canceling the 1 plus cosine x terms, we are left with negative sine x in the numerator and sine x squared in the denominator. 1 power of sine x cancels, leaving us with negative 1 over sine x. This simplifies to negative 1 over sine x. We know that the reciprocal of sine x is cosecant x. Therefore, the final answer is negative cosecant x. And so, we have proved the result using direct differentiation. Now let's explore an alternative, often simpler method. We'll call this Method 2, using logarithm laws. This method relies on the logarithm law that states the logarithm of a quotient is the difference of the logarithms. This is a very powerful tool in differentiation. Let's apply this to our function y. We can rewrite y as the natural log of 1 plus cosine x minus the natural log of sine x. Notice how this has transformed a complicated quotient into a simple difference of two functions. Now differentiating is much easier. We differentiate each term separately. The derivative of the first term is 1 over 1 plus cosine x times its internal derivative, which is negative sine x. The derivative of the second term is 1 over sine x times its internal derivative, which is cosine x. This is the chain rule applied to two separate natural log functions. Now we need to simplify this expression. We have a difference of two fractions. The next step is to find a common denominator, which is the product of the two denominators. We multiply the first fraction by sin x over sin x, and the second fraction by 1 plus cosine x over 1 plus cosine x. This gives us a single fraction with a common denominator. Combining the numerators, we have negative sine squared x minus the quantity cosine x plus cosine squared x all over our common denominator. Distributing the negative sign gives us negative sine squared x minus cosine squared x. Once again, we see the term sine squared x plus cosine squared x, which simplifies to 1. Factoring out the negative sign from the numerator helps us see this clearly. This gives us negative of 1 plus cosine x in the numerator. Now, just like in the first method, we can cancel the term 1 plus cosine x from the numerator and denominator. The result is negative 1 over sine x, which is negative cosecant x. As you can see, both methods give the same correct answer, but using logarithm laws can often be a much more efficient path. Now let's look at another example. This time, a very complex composite function. Our next problem is to differentiate the function y equals tan cubed of the square root of cotangent of 7x. The structure of this function is a power of a tangent of a root of a cotangent of a linear function. This is a classic case for the repeated application of the chain rule. It's like an onion with many layers. To make this easier to manage, we can rewrite the function with all powers explicit. Y equals the quantity tangent of cotangent of 7x to the 1/2 power, all raised to the power of 3. We'll differentiate layer by layer from the outside in. Here is the rewritten function, ready for differentiation. The outermost function is something cubed. We use the power rule first. The derivative is 3 times the base raised to the power of 2 times the derivative of the base. The next layer is the tangent function. The derivative of tan of x is sec squared x. So we have 3 tan squared times secant squared of the inside times the derivative of that new inside, which is the root of cotangent of 7x. Next up is the square root. We'll use the power rule again. The derivative of something to the 1/2 power is 1/2 times that something to the negative 1/2 power, times the derivative of the inside, which is cotangent of 7x. Only 2 layers left. The derivative of cotangent of x is negative cosecant squared x. This gives us negative cosecant squared of 7x. And finally, the innermost layer, the derivative of 7x, is just 7. We've reached the end. The complete derivative is the product of all these layers. The next task is to simplify. Here is the full, unsimplified derivative we just found. Let's make it look a lot neater. The goal of simplification is to combine constants, simplify expressions, and use identities to write the answer in its most compact form. First, let's group all the constant coefficients. We have 3 times 1/2 times negative cosecant squared 7x times the tangent and secant squared terms divided by the square root. This form is perfectly valid for many tests where simplification isn't required. But let's go further to practice our trigonometric identities. We know that tangent squared plus 1 equals secant squared. So, tangent squared is secant squared minus 1. Substituting this into our expression gives us this. While this might look more complicated at first, it shows that you can manipulate the expression in various ways. Another common simplification is to rewrite everything in terms of sine and cosine. This often reveals cancellations that are not obvious at first glance. Let's work through one last example to solidify these concepts. We want to differentiate e equals the square root of the quantity x squared minus 1 divided by x squared plus 1. This problem combines a power rule with a quotient rule. A good strategy is to rewrite the square root as a 1/2 power. This makes it a composite function. So, we have y equals the quantity x squared minus 1 over x squared plus 1, all raised to the power of 1/2. The outermost layer is the power rule, so that's where we start our differentiation. Applying the chain rule, we get 1/2 times the base to the negative 1/2 power, multiplied by the derivative of the inside function. Now we focus on the derivative of the inside, which is a quotient. We need the quotient rule again. Using our formula, the derivative of the inside is x squared plus 1 times 2x minus x squared minus 1 times 2x, all divided by x squared plus 1 squared. Now we need to simplify the numerator of our quotient rule result. A quick look shows that both terms have 2x in them. We can factor that out. Factoring out 2x, we get 2x times the quantity x squared plus 1 minus x squared minus 1. Remember to distribute that negative sign carefully. Inside the brackets, x squared minus x squared is 0. 1 minus negative 1 is 2. so the numerator simplifies to 2x times 2, which is 4x. So the derivative of the inside is 4x divided by the quantity x squared plus 1 squared. Now let's put it all back into our main derivative equation. We substitute our simplified derivative of the inside back into the main chain rule expression. Again, this is a valid answer, but we can and should simplify it further to get a more compact and elegant form. Let's start by using the exponent rules on the first term. The negative exponent means we take the reciprocal of the fraction, and the 1/2 exponent means we take the square root. The square root of a quotient is the quotient of the square roots. Now we can write the derivative as dx equals 1/2 times the square root of x squared plus 1 over the square root of x squared minus 1, all multiplied by 4x over the quantity x squared plus 1 squared. We can see some great opportunities for cancellation here. The 4 in the numerator and the 2 in the denominator simplify to a 2. This leaves us with 2x in the numerator and the square root of x squared minus 1 in the denominator, multiplied by the quantity x squared plus 1 squared. We can further simplify the x squared plus 1 term. The square root can be written as a 1/2 power, and the square can be written as a 2 power. 2 minus 1/2 is 3/2. So, let's recap what we've accomplished today. First, we successfully proved a trigonometric differentiation identity by using two different methods: the chain rule with the quotient rule, and the chain rule with logarithm laws. This demonstrated that there can be multiple valid paths to the same solution. And understanding logarithm laws can often simplify the differentiation of logarithmic functions. We also learned to systematically differentiate complex, multi-layered functions by applying the chain rule repeatedly, working from the outside in. Most importantly, we've seen that differentiation is not just about finding the derivative, but also about the skill of algebraic and trigonometric simplification to present the answer in its most concise and useful form. Thank you for watching this tutorial from Math Zone African Motives. If you found this helpful, please subscribe for more in-depth maths and physics tutorials. See you next time. Subscribe for more tutorials from Math Zone African Motives.